This video is designed to show construction instructors and students how Babylonian builders might have calculated the area of a circle more than 2,000 years ago, and why pi r squared is the formula for the area of a circle. Now, we all know that the area of a circle is calculated by multiplying pi times the radius of the circle squared, but why? Have you ever wondered why? In our hurry-up lives, thinking about why pi r squared gives us the area of a circle probably isn't high on our to-do list, but if we slow down for just a moment, I think doing so will give us insight into much more. But before we get started, let's get a few definitions out of the way. A circle, a curved figure with all points in equal distance from the center point. A chord is a straight line from one point on a circle to another point on a circle. The longest chord is the diameter. Circumference, the perimeter of or linear distance around the circle. Diameter, the straight line segment from a point on the circle through the center to another point on the circle. Radius is 1/2 the diameter of a circle measured from the center to a point on the circle. And now back to the question at hand. Why does pi r squared give us the area of a circle? Well, we can use integral calculus to explain it, but we want to do it like the Babylonians. So let's take a closer look. Let's start by calculating the circumference of a circle with a diameter of 1. And let's not worry about the unit of measure. The diameter is just 1. It could be inches, feet, miles, doesn't matter. If the diameter is 1, then the radius is 1/2 that length, or 0.5. And we will use 3.1416 as the value of pi. Let's go ahead and calculate the circumference of our circle the way we usually do, using 2 pi r, or another way of expressing the formula is pi d. When we multiply pi times the diameter of 1, we get a circumference of 3.1416, and we can round that to 3.14. Now let's solve for the circle's area. Pi times the radius squared, which is pi times 0.5 squared, or 3.1416 times 0.25, which gives us 0.785 as the area of our circle. And keep in mind that that 0.785 is square. It's 0.785 square inches or square feet or square miles. Again, we're not going to complicate things by worrying about the units. Now, I said in the beginning of this talk that we would figure out the area of a circle like the Babylonians, and I meant it. The reason we just calculated the circumference and area using our normal means that we usually do is because we wanted to have the right answer to test our Babylonian theory against. Now, let me show you what I mean. Let's clear our heads for just a moment and forget that we know pi r squared. We're Babylonians. We don't have calculators or a circle area formula. We do know how to get the circumference of a circle as long as we know the diameter, but without all the modern knowledge and equipment, how will we find the area of a circle? Well, what if we break the circle into smaller parts and reassemble it so that it's more like a rectangle or a parallelogram? Now, even the Babylonians knew that if they wanted the area of a rectangle or a parallelogram, they could multiply base times height. But the circle was more elusive. So let's look at our circle again. How can we divide it into smaller sections? We can divide it into pie-shaped slices, can't we? Let's start with a simple example. Let's divide it into 4 quarters. Now let's take them out of the circle and rearrange them so that they're lined up horizontally. Since the circumference of our circle is 3.14, the 4 arc lengths still add up to 3.14. Now, in order to get the shape of a parallelogram, let's add 4 identical pie cuts upside down and in between. Now it looks more like a parallelogram, doesn't it? The problem is we have a lot of area that we can't account for and not enough information yet to know the parallelogram's base and its height measurement. If we could flatten out the arcs of our pie cuts, we could use their combined lengths as the base length of our parallelogram. Remember, no matter how many pie cuts there are, their combined arc lengths equal the circumference of the circle. What if we divide the circle into more than 4 equal pie cuts, maybe 16? We take those 16 slices and arrange them like we did before, add 16 ghost slices between and below. This looks even more like a parallelogram, doesn't it? The arcs are much flatter. Let's go even farther. Let's divide it up into 36 pie cuts. We arrange the pieces as we did before, add the ghost pieces to fill in, and now we have something that really looks like a parallelogram. But let's see if we have enough information to calculate the parallelogram's area. Let's start with the height. Well, it looks like the radius of the circle, 0.5, could be close to the height of the parallelogram. In just a few moments, we will take a closer look, but first let me stop for just a moment and say that I don't want to burden you with a bunch of calculations. I just want you to see that the radius looks like it could be used as the height of the parallelogram. I'm going to show you some blown up views of our pie cut in just a moment, but don't get bogged down in the minutia. Remember, you are a Babylonian without the luxury of CAD programs and calculators. I'm just giving you the inside scoop to help you visualize how we get a circle inside a parallelogram. As we zoom in on the pie cuts, we can see that the radius of our circle is slightly less than the height of the parallelogram. Can you imagine how close we could get if we divided it into 360 pie cuts, or 1,000, or even 1,000,000? But for now, our radius of 0.5 looks close enough to use as our parallelogram's height. So what about the length, or the base of the parallelogram? The base is the sum of the 36 arcs that we rearranged to make a parallelogram. And their sum is 3.14, right? To put it another way, the base of the parallelogram is 2 pi r, the circumference of the circle. Let me say that again. The base of the parallelogram can be thought of as 2 pi r, the circumference of the circle. Now don't forget that these arcs are still curved lines, not straight lines. But as we increase the number of pie cuts, we flatten out the arcs, getting closer and closer to the actual base or length of the parallelogram. Let's find the area of the parallelogram, which will lead us to the area of our circle. So we take the circle and divide it up into 36 pie cuts. It could have been 72 or 100. I just chose 36. We rearrange them so that they're laid out horizontally, and we double them so that we have a parallelogram. Let's not forget why we rearrange the circle parts to take the shape of a parallelogram. It's because it's a shape that we can easily deal with. Base times height equals area. And we said the circumference of the circle is 3.14, and with it laid out horizontally, it still is 3.14. I know I've said this over and over again, but I want to make sure that you understand that the circumference of the circle is the base of our parallelogram. And we said that the radius, 0.5, of our circle would become the height of our parallelogram. So now let's solve this easy area problem, base times height. 3.14 times 0.5 equals 1.57. The area of the parallelogram is 1.57. And now for the money shot. We've calculated the area of the parallelogram at 1.57, but remember, we put in 36 pie cuts and 36 ghost pie cuts to get the shape of the parallelogram, right? So to get the area of the circle, all we have to do is divide by 2 to subtract out the ghost pie cuts. And this gives us 0.786 square inches, square feet, square miles, or whatever unit we're using for the area of the circle. Now let's revisit a slide you saw towards the beginning of the presentation where we calculated the circle's area using our calculator. The calculator version of our circle area is 0.785. Our version, the Babylonian version, is 0.786. Not bad, huh? Well, what would account for the difference? Well, different rounding is probably the reason why it's different. Remember, we used the arc lengths of those 36 little pie cuts, and the arc is longer than the straight line distance. So that would account for why our version was slightly longer. But they're certainly both close enough to order carpeting or multiply times the depth and order concrete. Now back to the original question. Why is pi r squared the formula or the area of the circle? Okay, we have a parallelogram where half its area equals the area of our circle. Remember, 2 pi r equals the circle's circumference and also the base measurement of our parallelogram. So let's substitute 2 pi r for base and the radius for the height. To find half of the parallelogram's area, we divide by 2. The 2 cancel out, leaving us with pi times r, and if we simplify the equation, drum roll, we get pi r squared. And that's why pi r squared is the formula for the area of a circle. Now, to some of you, this exercise will seem stupid or a waste of time. How could I use this? What's this good for? Well, I'll tell you. This exercise is about pi r squared, sure. But actually, it's more about taking something apart that you can't define and putting it back together as something useful, something you can define. It's about seeing things through a different lens. In Kurt Vonnegut's book, Slaughterhouse-Five, he likens our awareness in life to lying on our back in a boxcar that's moving down the rails and having our vision limited to what we can see through a 1-inch hollow tube that extends vertically through the roof of the boxcar. Now think about that for a minute. Think of what you're seeing through that 1-inch tube and what's actually going on all around it that you can't see. I read this 45 years ago, and it had a profound effect on how I approached solving problems. I'm not talking about just math problems, but any kind of problem. Take it apart and rebuild it so that it's no longer a problem, but something useful. Look beyond what you see, looking through the 1-inch tube. Okay, I'll get off my soapbox, but try explaining the origin of pi r squared to your classmate or to your parents. Simplify what I did in the video so that you can explain it on a napkin or a scrap of paper. It'll be fun. You'll understand more about pi r squared than you ever did, and this technique may come in handy in the future. Good luck, and I'll see you on the next video.